In fact, no, without a zeroth law and thermal equilibrium, it is impossible to do anything with the thermometer, starting from manufacturing to printing the scale to anything. So I want to give one more important application. Let us say there is a company which is making the something like production of thermometers, any kind thermometers. They want to produce a thermometer, let us say liquid in glass thermometer for the sake of industry purpose, industrial purpose, not just for medical purpose, whose range is very small. Now what they should do, they should buy a standard thermometer. Not, okay, it's going also. So they should buy a standard thermometer. Okay, mostly these standard thermometers for industry may be supplied by some government organizations. Suppose if I take India, it could be something like a Bureau of Indian Standards. Now they'll procure a standard thermometer. Most probably this could be what is called a platinum resistance thermometer, which I'll tell you what is it, or many of you may be knowing from school. Afterwards, now he has to select, okay. After doing this one, he has to select an environment. First, he should have an environment which creates various temperatures. Okay, maybe that could be a beaker with a distilled water so that it is a pure, okay, pure water. Okay, and the moment he has a pure water, and he'll immerse what is called standard thermometer procured from the Bureau of Industry, that is standard thermometer. Okay, now he produced some thermometers. Now he has to print the temperature scale on this. So then what will he do? He will, whatever thermometer which he made, something like a alcohol thermometer or a mercury thermometer, all of you have seen there will be a small reservoir, a capillary, a bulb with a lot of fluid in this. Okay, so he made everything. So now he has to have an equilibrium. This is what is called a new thermometer made by him, which requires a printing. Where is 0, where is 10, where is 100, etc. Let us say he is interested in only 0 to 100 degrees Celsius, for example. Okay, first how can he produce a 0? So with the distilled water, what he'll do is he'll put some ice blocks. Okay, then he may probably insulate everything. After putting ice blocks, he'll insulate. These are the ice. Okay, there should be a space above this one. It should not be completely filled because some amount of vapor of steam may also occur. So he'll insulate everything. Okay, something like this. Then what should he do? He should wait for a reading on the standard thermometer, the reading level of alcohol or a mercury in the new thermometer. Maybe the standard thermometer will have a computer control. On a computer, it will display some units. I am looking for 0 degrees Celsius displayed here as a digital. So he has to wait for quite a good time till the standard thermometer shows a 0. And also at the same time he has to see the new thermometer, and he should wait till the level of alcohol in the thermometer doesn't change for a long time. Now you see this one, beauty of this one, this is A. Okay, this is A and this is B and this is C, isn't it? A is the standard thermometer, B is the new thermometer to be calibrated, sometimes it is said, or to be inscribed with the scale, and A should be compared with the B. Without comparing with the A, B cannot work at all. No industry on this globe can use this one unless there is a scale on the B. Now I want to print a scale on the B. I have a A. Without having a C, how can I print? How can I create an environment? Now you see this one. If you see, the moment I weight it, there is a minimum level in this one, which he'll say 0 degrees Celsius. Isn't it? So what is the situation now? The level in the alcohol or a mercury thermometer is stationary. The digital thermometer signal is stationary, not at all changing. Now what is the thing? A is in equilibrium with the C, B is in equilibrium with the C. Then I'll say A and B are in equilibrium. Whatever temperature sensed by the standard thermometer is same as what is sensed by the new thermometer. And whatever level shown by the new thermometer is 0. Now I don't have a doubt. You see this one? Can any industry on this globe make a thermometer and sell the thermometer, get it certified that we have made a world-class thermometer without following the zeroth law? Isn't it? So this particular thermometer, again, 0 is not sufficient. Maybe he'll heat entire thing. This temperature will go on increasing. Let us say this is subjected to an atmospheric pressure, P atmosphere. Then again it will increase. Suddenly when it reaches what is called a boiling point, for a long time there will be a equilibrium because a lot of water is getting converted into steam. I have a lot of water. So now because change of phase occurs at a constant temperature, now you see the standard thermometer is in equilibrium with the system C, and the moment the level in the one reaches the maximum, it is not changing. When this is showing 100, I'll say this is 100. Okay, afterwards I'll divide in between to whatever scale I want. Somebody may be interested in 1 degree resolution, somebody may be interested in 0.5 degree resolution. Somebody says, I'm doing an industrial measurement, I don't need such a fine measurement. 10 degrees Celsius step is sufficient. Now you imagine a thermometer cannot be made without A, B, C. Now same thing I told you, when the doctor or a medical person uses or industry person uses, he is comparing a product with the another product, or he is doing one system with the another system. It looks like the making, calibration, and anything you talk about the temperature measurement, it is impossible without having a zeroth law. Zeroth law talks about only thermal equilibrium. Why? Because when two systems are in thermal equilibrium with each other, only one thing that is obviously same is temperature. But there are other equilibriums which are little confusing and elaborate, which I explained last class. That's why people do not use any special law. But this zeroth law understanding will help you in measuring all the parameters on the globe. And there could be many equilibria to be satisfied. So some of the equilibria which are very popular with respect to thermodynamics, I was showing you in the last class. Mechanical equilibrium, where the force, pressure, torque are measured, and there are some exceptions which I showed you. And another important thing which arrived very interestingly, perhaps relatively younger you can say, is the chemical equilibrium. Now you can see this particular chemical equilibrium. Without a chemical equilibrium, the modern processes will be of low quality. You imagine, let us say somebody is making some kind of food or a pickle. And if I say that I don't want any kind of instrument to measure at all, so he'll have somebody who will taste and say that it's salty. Somebody who is tasting the same thing, because he has an habit of taking more salt, he'll say, no, it's not salty. As some person who takes intermediate will say, it's okay, moderately salty. Can you develop a process standardization just a descriptive understanding? Impossible. Even if I want to know whether it's a salty or a sour or a bitter, there has to be a quantitative measurement. How do you develop a quantitative measurement? The quantitative measurement of a concentration requires a chemical equilibrium. A system is in chemical equilibrium when there is no tendency for quantities of that particular species is not changing. Now you imagine, suppose if I take some amount of pickle to taste, I put immediately say salty. No, 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 no. I have to wait for some time. Why? My sensors on my tongue should reach an equilibrium with this and come to a conclusion whether it is salty or not salty. And if it is too hot, no, with a small signal, your sensor gets bad. No, 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 I can't test it. But still, it is not in equilibrium. So it is impossible to sense the taste, smell, which are due to the concentration of the chemicals without a chemical equilibrium. So that's how the zeroth law also creates a route for the chemical equilibrium. What is this? When two bodies have equality of concentration with a third body independently, and I can say that these two bodies are in chemical equilibrium with each other. So the chemical equilibrium talks about the equality of the concentration. But equality of the concentration has 1,000 million different concentrations being equal. So that's why people cannot say that you can say that when two systems are in chemical equilibrium, the concentration of one species is same. What is that species? I need to know. So that's how any species, when they are in equilibrium, they will be in chemical equilibrium when the concentration is same. So the chemical equilibrium develops many modern instruments. Just for example, what is the implication of such a invention, chemical sensor? I told you about the fire alarms, etc. I'll give you one of the wonderful research done in Japan by the forest department. So they have developed what is called a chemical sensors with a very good aptitude. What is that good thing? Okay, so can we selectively detect these chemicals? So there is no doubt there has to be a chemical equilibrium. But I need to know my sensor is in chemical equilibrium with system A. What kind of species which is responsible for the equilibrium? You need to know. Means you need to basically make what is called the classes of chemicals. Not only equilibrium. What is it equilibrium with? See the beauty. When it is a thermal equilibrium, a zeroth law, if they are in thermal equilibrium means it is obvious, temperature is same. So when it is a chemical equilibrium, a chemical sensor, no doubt, A and B are in chemical equilibrium. But what is that species because of which they are in chemical equilibrium? Like the way I said, no, equality of temperature, equality of concentration of what? So you see this one, it gives some more and more opportunity for further research. So the people now literally developed what is called electronic tongues, electronic nose, so that you will have a more quantitative description, not a qualitative description. I said, chemical sensors covers a wide range of devices to monitor, measure, test and analyze the concentration in many of the purposes and many other things. Now you see, this is the example what I was giving. You see, Japan is a small country and their green forest is also very small. But as a nature, behavior of a nature is on and off there are fire accidents, because of which there is a massive destruction of their small natural habitats. So they said we can't tolerate. We should know why these are occurring and try to control them by helping them. So that's how, what did they do? They did a research. The research led to this fact that any forest continuously sheds dry leaves, some sub branches, some dry fruits or many things. All these things now get stacked together. All these are biological food. These are some kind of carbohydrate structures, maybe cellulose, maybe sugars, maybe proteins, many things, because of which bacteria will start acting on them and they get decomposed. There is a combustible methane which is released in the air. So because of this particular one, whenever the methane concentration increases in the air, it automatically ignites. There is a big forest fire. So they wanted to know, can we detect, and whenever this concentration is reaching a critical, I should send some people to remove all these dry leaves or throw some water wherever it is going to, or do something to protect a massive firefighting. You see this one, they need to develop a device which will go into equilibrium with the methane in the air, whatever is the concentration. Okay, so what did they develop? You see this one. So as a part of research, they have developed what is called a bugs. These bugs, like an ordinary natural bug, they'll fly continuously in the forest. But these are electronic bugs. So whenever the methane concentration increases, they'll give a beep, beep, beep alarm into the control room very far. You can use the microwaves or any other way of communicating. Now you see, because of this, whenever they get that alarm reaching the critical thing, they'll send the people throw water on the spot and try to clear the dry mass. Why? Clearing a dry mass regularly in the forest may not be economical, may not be good also. Why? Every tree try to recycle some of the nutrients from its own rejection. You cannot work against the nature. If you start removing them, you may stop the forest fire. The growth of the trees will be curtailed. Now you wanted to do good, you will do a bad thing. So that's how, only when it is a dangerous level. What is the meaning of that one? They have a excess more than what they can recycle, they should be removed. You see this one, the every equilibrium, every quantitative description that I am saying, the zeroth law, a mother of all the laws, based on the truth that two systems, when they are in contact, they'll try to reach equilibrium. Sometimes I don't want them to reach equilibrium. Sometimes I want them to reach equilibrium as early as possible to take a decision. What is the application where I provoke, promote, try hard to reach equilibrium as fast as possible is only one, that is measurements. It could be pressure measurement, temperature measurement, anything you say, they have to reach in equilibrium. See the wonderful thing, unless you quantitatively describe, what decisions you can do? Nothing. All your decisions are useless. So that's how thermodynamics has such a beautiful thing. I'm talking about thermodynamic equilibrium, which is different from thermal equilibrium. Thermal equilibrium is the focus of zeroth law. But thermodynamics is not just thermal equilibrium. It has to do many things. You need to be very careful. Thermodynamic and thermal. The people unnecessarily make a mistake when they state the zeroth law, thermodynamic equilibrium. Zeroth law cannot talk about the thermodynamic equilibrium because it requires many equilibria in general. So that's how, finally, after knowing these equilibria, when a system is in equilibrium, regarding all possible events, it could be, as I said it now, I may or may not be knowing, sometimes I think I am in equilibrium, there is some subtle thing happening which I don't know. So then every time when I measure that quantity, it is coming differently. Why? There is something unknown which I don't know, that is also an equilibrium to be satisfied. Then obviously you will make a mistake. All of you know very well, you go to a lab, all of you are doing the same experiment, it may be chemistry lab, physics lab or a engine lab, anywhere, or all of you are doing the same measurement, but each one of you get a different results. Why? All of you are not well trained to know what are the possible equilibrium before I say that this is the reading. So you have to develop a lot. So that's how a thermodynamic equilibrium demands all possible in general, but more specifically, very transparently, a thermodynamic, two systems are said to be in a thermodynamic equilibrium when they are in chemical, mechanical and thermal. Yeah, thermal, mechanical and chemical, whatever we sequence which you love to state it. So the properties of system can be then only measured. So you cannot measure, though I am measuring a temperature, the best way is perhaps to have the thermodynamic equilibrium, then you can have the complete description. Many times it may not be possible, but to that level there is a accuracy error analysis coming into. So the definition of a system using certain observable macroscopic properties. So finally what I am concluding is why I want a zeroth law, because quantitative description of system is essential to state that I can do something. I have understood this system. So to have a quantitative description, okay, what do you need to have? You need to have a measurement. And what do you want to measure? You need to decide what is good to measure. What are those things which can be measured? Macroscopic properties, macroscopic characteristics. For example, pressure, temperature, volume, which will come into us very easily, or density. These are the ones which are called primitive properties. Whenever I want to measure this one, I don't have to spoil the system at all. But your knowledge is insufficient Unless you go beyond this one, you need to know much more than these to do a job. In fact, no, to take a more and more innovative decisions, one have to understand more properties than these three. So this is where the important thing. So suppose if I say I have completely defined the state of a system, how many are required? This I explained you uh, last class about this one as a state postulate. I am reminding. What is the state postulate says? Suppose if the system which I am studying is a simple, means no viscous effects, no magnetic effects, no electrical effects, etc., and also contains a pure substance, then you need to know only two properties. The moment you fix two properties, the system will be completely defined. Any other property, can be calculated using these two properties. You don't have to measure everything at all most of the time. No doubt, only these two properties are not sufficient for to take a decision. But to know the state, two properties are okay. Using these two properties, I can construct a mathematical model to know third property which I can't measure, but I want to know, otherwise I can't do anything. Very important. Knowing the system doesn't mean that only two. You have to know more. But to say that I have completely described means two measurements should be stated. Or if I want to fix the state of a system, if I fix any two properties of this simple substance, then I can say nothing is happening because I have fixed these two. There can't be anything at all. And any other property, you just calculate one after the other. I don't have to do anything. You see the beauty of this particular one. So finally, I am concluding the measurement, quantitative description, and the knowledge in a consolidation. Properties of a thermodynamic system are the ones which will help you in quantitative description of a system which you want to study and which you identified from the entire universe by drawing a boundary. Now you are studying, you are understanding because you want to do something good to that particular system. A system should be described using a set of point functions or properties. Okay, the moment I do this particular point function, the change in these functions can be calculated without performing any action. Okay, I don't have to do any kind of creative action to know what could be the change of A, what could be change of the B. You can always predict, you can always calculate without doing the action also. That is the greatness of this one. So one can have instruments. So whenever it is a point function, whenever it is a property, and you will always have a way of developing an instrument. It is almost impossible that you say this is the property of a system, but I can't measure because there is no instrument which can measure. That is time being. Maybe you don't have that much intelligence to develop that instrument, but the moment you think you have identified as a property, there will be an instrument which will measure. Sometimes what happens, no, you measure something, but calculate whatever you want using those measurements. Okay, always there is no rule that you have to measure only that particular property. You can calculate by measuring other characteristics. Now, what is the beauty of this one? So you are working in an industry. What is the property of this one? Property of this one? No. You go to any industry which is making the turbines. They are making the day in day out crores and crores worth of the turbines. They may be supplying all over the world, but they will not measure the steam properties every day, see what is the property, if the pressure is this, temperature is this. No, no, no. They'll buy from a sorry, a standard organization and they'll get the tables. Now, okay, I want to design a turbine at this pressure and temperature. What should be the volume? And what should be the size? All these things means because you have defined a property very perfectly, somebody somewhere in America will measure the properties, make a table, and I'll believe that those tables are correct and start designing the turbines and send all over the world. Why? Because everybody is strictly following the law of equilibrium. A zeroth law for a thermal and mechanical, chemical or whatever it is. Because everybody is perfectly following, I don't have to measure my properties again and again, though I am using that steam 1000 times in my life. Okay, in fact, no, today I'm leaving for Bangalore. This is a company called a Maxwatt Turbines Limited. They're making a small turbines. I was surprised to know that this company is exporting hardware turbines to Japan, North Korea. Whole world is procuring from them. I felt proud. Now they want to enter into a new product where we did some research. So we are now working together. So then, okay, then as a initiation, no, a month back I delivered a small lecture on a philosophy of innovation. Now, can you believe they have 150 engineers? The owner of that company says, ki, no, sir, you please come and spend 5 days. You teach whatever thermodynamics you are teaching, no, teach us to again. Now we know how to innovate. We understand everything, but we think we haven't understood the fundamentals. That's why we are not developing a quality products. That person says ki we want to stand in the front in the entire world. That's why we want to listen to you. Can you believe the 5 days continuously? I'll teach them same course which I am teaching, but can you believe the senior most who is going to be my student is double my age, and the junior most is half of my age. Big spectrum of students. Why I am saying all this particular one is the function tables are developed, properties are calculated, used or reused all over the world because everybody follows that theoretical concept. And every company will have a training program so that their engineers will not forget that this is the basis for the development. Very important to understand. Going ahead, any industrial process can use these properties. Now you see, I'm going to a company which produces a steam turbine. I'll talk about all these things to them. And last week, I visited a company which is producing some kind of, what exactly I say those projects, boilers. I delivered a lecture to them. And you imagine, what I'm teaching is same subject. But industries are different because every product requires this knowledge. Why I'm giving this example is what you are learning, no? If you learn perfectly, it will help you lifetime to achieve great things. So this is the function which we proudly call a property in thermodynamics. So somebody measures for me and I'll buy the properties. Using those properties, I'll construct products. And he knows how to measure, but I don't know how to measure. But I know that he is following the rules, and I know what are the rules he has to follow. And using these properties, yesterday there was no turbine, today I have developed a turbine. Why? I have used those properties to create a new product. You imagine, you believe me or not, without knowing the properties of the substance, there can't be any innovation on this globe. Every innovation requires understanding properties of materials, chemical, thermal, etc. Without understanding a property, there is no innovation at all. What you are doing is nonsense if you know nothing. So finally coming to the most interesting part of this, because thermodynamics mostly talks about a simple substance. Why? Because this is taught to a first year or a second year engineering students. If I consider a complex substance, they have to learn lot more sciences to understand. Suppose if it is a simple substance, without having a lot of experience also, you will get this concept. That's why, you should always believe your teacher that why he is talking about a simple substance always. Not that he doesn't know, not that this subject is limited, because you are very young, you have hardly any experience to understand a complex substance. But your confidence level should come. That's why I'm taking only simple substance. What is that simple substance I said? And there is another way of defining a simple substance. Most of the simple substances, if you measure any property, or many simple substances will have some properties which are directly proportional to temperature. This is a nice characteristic of these simple substances. Suppose if I take an ideal gas at a constant pressure, volume will be directly proportional to temperature. Suppose if I take same ideal gas, keep the volume constant, and pressure will be proportional to the temperature. Very nice, no? So all these things, there are many substances which are directly proportional, and because of that, I can measure the temperature. Otherwise, temperature I can describe, only effect of temperature can be measured. I told you, very important. This is the reason Initially I thought I should not discuss about the measurement, but at least temperature measurement I'm discussing because it is very important to understand how to measure things, because most of the macroscopic properties cannot be directly measured, but the effect of those macroscopic properties can be measured. And as I said it now, only one thing I can measure is the length. Suppose if the temperature can produce a length effect, I can measure it. What for that one, what did I select? I have selected a volume expansion of liquids. The moment I select the volume expansion of liquid, whenever there is a temperature change, the volume decreases or increases. So a change in volume is directly proportional to the temperature effect. So actually I say I have measured the temperature. I did not measure the temperature. What did I measure? I measured only the effect of temperature. What was that one? There is a increase in the level. You see the beauty. In the entire world, only two things can be measured. What is this one? A physical displacement or a counting number 1, 2, 3, 4, 5, 6. So that's why now sometimes people know the modern world, anything they'll convert into digital numbers. Okay, so what is the meaning of a digital world? 100 degrees centigrade is divided into some digital numbers 1, 2, 3. You count something, and higher the temperature, there should be more counting. Why? Humans cannot measure anything other than quantitatively the displacement or numbers. So whenever I want to measure a property, that effect of that property should be translated into either displacement or numbers 1, 2, 3 like a digital world. Okay, there are digital thermometers which will give one number for a small change in effect of temperature. So that's why I need to know all those substances which will help me to give a nice effect due to the change in temperature. Then what will happen? I can have a temperature measurement anywhere. Let us say there is a company which is producing nuclear power. There is a nuclear reactor inside, and I need to measure the temperature of the reactor for the sake of safety. Can I go and measure and physically? No. I have to be very, very far from the reactor. Still I want to measure. And this particular sensor should be in equilibrium with that one. So ordinary liquid in glass will not help me. I have to do many things. That's why I know the first step in measurement of any property is to understand. So the properties, so the substances which have a direct proportion, the property, any substance which has one property which is directly proportional to temperature. Those are called thermometric substances. You imagine, you have learned many things in physics. Thermophysics is such a beautiful thing. What is this one? The resistance is one such property. Resistance of many materials are proportional to temperature. Some are weakly proportional, some are strongly proportional. Which are the best? The metals. So whenever you change the temperature of a metal, the electric resistance changes very good. So that's how people started using those. What is the advantage of that particular one? Measuring the resistance is through electrical signal. That electrical signal can be digitized, can be transferred to the computer, store it. And because of which what will happen? Thermometer is somewhere 2 kilometers away from me. I am sitting in a control room happily looking, and whenever something happens, no, I do something and bring back the temperature, then I say I am controlling the reactor. Though I am running away from that fellow, I fear to go, but I think I have a command on that one. All these things requires more and more properties to look from a far or anything else also, not only farness. There could be many other demands. Any other simple property, as I said it now, not only the volume expansion, not only the pressure, there could be many properties. Any other simple property which varies with the temperature is called the thermometric property. And depending on the number of thermometric properties, you can have a more and more. You see this one, nowadays there are so many diseases which are contagious. Many times no doctor cannot touch them even. And if I use an ordinary thermometer, keep in a mouth and take it, whatever may be the cleaning, some of the bacteria I cannot kill them. Now if I test one such patient, all other patients who have ordinary diseases may get affected. Then what should I do? If you go to the modern hospitals nowadays, they have a radiation. What the doctor said, open your mouth, she put a small light, and she gets the temperature. Now it is not getting contagious. So now I need to measure a property depending on the system problem, a difficulty. Even the doctors are using what is called a radiation type and non-contact. You are not contacting at all. Because of that one, what will happen? It is thermally equilibrium but not touching. Suppose if I touch it now, what will happen? Along with the thermal equilibrium, it may like to have a chemical equilibrium, but patient and thermometer chemical equilibrium means whatever microbes and bacteria which is affecting the disease, that will also be getting accumulated on the thermometer. I'm not sure whether I have some chemical to clean it or not. Now what I am doing, by doing this one and on contact, these two are in thermal equilibrium, but I am not caring about other equilibrium because temperature measurement, taking a decision is enough. Afterwards, I'll take the blood and do more tests. I'll take the urine and make the more tests. Once I get an initial doubt, I can do more tests. And I'll not do only this one. You see this one. Very important to have many such properties to have a temperature measurement or anything else. Out of all this, do you know, all of you know why ideal gas is so popular? Why the whole world looks or any subject talks about ideal gas equation? Because this is the one which facilitated the measurement of temperature in most correct way, the best way. Okay. So that's how ideal gas is called a good thermometric substance. And you can see this particular picture which I am showing here. So this is the picture which I am talking about, a kind of a constant volume or a constant pressure. I have, suppose if I lock the piston and heat it, it is a constant volume. Suppose if I free the piston, then what will happen? Pressure is constant, volume will vary with respect to the temperature. Let me show you some of the constant volume ideal gas situation. The relation between the pressure and temperature, if I want to establish, you see this particular one. So this I am using it as a constant volume. The piston is locked, you can say. Okay. Can you give a pen, small thing? Let us say I'm locking here. I'm also locking here. Because of the locking, now whatever you do, piston cannot move. What does it mean? It is a constant volume. Now what I am doing with this particular system, with this constant volume, I am doing this. I am heating it. Because I have locked this one with the constant volume, okay, so volume will remain constant. Now I'll go on doing and try to reach another equilibrium position from 1 to 2. You can see this particular one. Now the moment I keep the volume, because I have taken an ideal gas, now the T2 will be greater than T1. Because T2 is changing, what will happen? The pressure will change. So if I have something connected to this which will measure the pressure, then I can measure the temperature. Actually I am measuring only pressure. I am not measuring the temperature. Now how do I measure the pressure? Something should get displaced. Why? I only measure the physical displacement, nothing else. Now you can see the simplicity of this ideal gas. The P1 by T1 is equal to P2 by T2. The P is directly proportional to T. Just by measuring the pressure, I can get the temperature. And how do I measure the pressure? The effect of pressure should easy to translate effect of pressure into displacement. I told you. The people could easily measure the pressure. Why? Displacement measurement was easy. The moment I measure the displacement, what can I do? I can take a balance and match the displacement. I can measure the force. The moment I can measure the force per unit area is pressure. The pressure is more direct than the temperature. Temperature is much more deep and complicated but very essential. And without temperature, there can't be any decision taken on this globe, perhaps. According to my understanding, there is no science or a engineering or a psychology where that without temperature they can take a right decision. Now you see this particular one. Suppose if I double the temperature effect, there will be double in the pressure. Why? You see this one. The amount of number of moles of ideal gas is constant because it's closed. and the volume is also closed, constant. Why? I am locking it, because of which these two will be directly proportional to each other. I have created a very good thermometer which will convert any temperature effect into a pressure. Of course, that pressure should also be measured using a displacement. Okay. Now, why you need to understand, whenever I heat it or do it, why the temperature is changing? Because temperature is such a sensitive quantity which varies a lot. Okay, sorry for this. Okay. Now you see this particular one, whether it is a solid or a gas, maybe liquid in between. You know that in a solid, the molecules are arranged in a crystalline form in a specific points. So whenever I increase the temperature, no, this particular molecule or an atom, depending on the kind of solid, will try to oscillate about a mean position. Higher the temperature, more will be the amplitude of the molecule. Can you believe, after all, what is the temperature? Microscopic rate of displacement of a molecule is the temperature. So the temperature directly affects a microscopic displacement, but outside we can't see. We can see only there is an increase in volume. Why there is an increase in volume? All the molecules are vibrating with a higher amplitude. They need a more space. That's how there is an expansion. Okay, so you can see this one. Suppose if I have a gas, these gas molecules, all of you know, moving randomly with time. All of you know this one. All the molecules move randomly. Their velocity will be random function of time. That's why I'm drawing here random function. Suppose if I increase the temperature, what will happen? So you see, initially they are vibrating around a mean line. Now they have increased to higher level. Even for a gas, higher the temperature, the velocity of the molecules will be higher. All of you know from your microkinetic theory of gases. What is after all the temperature? The great Boltzmann. So that's why the Boltzmann is such a superb scientist. Something which we cannot visualize. We can only see macroscopic effect of temperature. Can you believe why this fellow is hot? Because these molecules are hitting more faster my fingers. That's why I'm feeling hot. Isn't it? Suppose if I'm hotter than the material, what will happen? My body molecules are hitting that one much higher amplitude. That's why I feel chill. Can you believe? The only Boltzmann is such a great scientist who worked with this and developed a microscopic event. That's how no. What is the temperature really? Why I'm talking so much about a temperature? No, the temperature is such a quantity which cannot be directly measured. But the effect of temperatures are very powerful. We have to measure them. And that's why one gets an idea why this temperature is affecting so much. I'll give you one of the most powerful example of the importance of temperature. If you go to the website of Austria, in Austria there is called a University of Austria. In a biological department they have a biothermodynamic department. And they are doing a funny experiments how the temperature affects the biological systems, which many of us know. Can you believe? Out of their research they found that the sex of a baby can also be affected by the temperature. But when it comes to the humans, no, it is not a big function. They could not conclude. But they found some species, and mostly these are crocodiles and turtles. Can you believe that turtles and crocodiles, the sex of a baby depends upon the temperature at time of delivery. If the temperature at the time of delivery is less than something, it will be female. And if the temperature of the environment during the delivery is higher than something, it will be a female. For turtles, it is opposite to the crocodiles, means lower temperature below is male, higher temperature above is female. Similarly, the crocodiles, the inverse of that. But we are most stupid, what I say, enthusiasts. There are scientists, maybe that lab or something, they wanted to understand what happens if the temperature is in between that minima and maximum. They did an experiment. They found that most of the babies which born in a temperature above this minima and below the maxima, they were impotent. They were not productive at all. They didn't get a strong male or a female characteristic at all. Can you believe? The temperature is such a powerful thing. And if you say anything is not affected by the temperature, I strongly believe that we did not understand that physics. We have to learn more. Later or sooner, you will say, oh no, this is also a function of temperature. Such a powerful tool. So that's how the people wanted to understand. Very difficult to measure, but very obvious, very important to understand. That's how the temperature becomes so obvious in a thermodynamics or any engineering. That's how the Lord Kelvin came up with a scale which we'll learn soon. Absolute Kelvin temperature is proportional to average kinetic energy of the atoms. It is a measure of kinetic energy. Higher the temperature means the molecules are vibrating with a lot of kinetic energy. Inherently, there is a microscopic kinetic energy which is, this is the one. All of you know the T is proportional to this kinetic energy per unit mass, and which can be equated to half kT, which you know very well from your discussion, which I am not discussing here. When atoms collide, they tend to average to equalize the kinetic energy spreads equally over the atoms. So that's how why system is reaching equilibrium, no? Why systems are reaching thermal equilibrium? Why it is a law of nature? Can you believe? So suppose if I see the honesty and sincerity or whatever say, openness of these molecules. Suppose if I have this particular body, I start heating this particular one, end of this, and this end is cold. So what will happen? This particular fellow will vibrate with a high kinetic energy and give something to the next row of molecules, next plane of molecules. These will take it and will give it to the other. So that's how whatever it is getting it will try to give it to everybody. Now why it is doing? It is a characteristic, democracy, equal rights. See, the substances without a life, they are democratic. We humans with a lot of intelligence, highly capitalistic. How nonsense, selfish. So this is the one. Law of equilibrium talks about the what is called a democratic nature of substances available in the nature. We are also substance. Unfortunately, we have a life, and that try to create running away from the equilibrium, isn't it? Okay. So this particular one, after all, is called a thermal equilibrium. So whatever kinetic energy, if somebody earns a more kinetic energy, what will do? Oh, I have more, I'll give it to my neighbor. And that fellow will give to its neighbor. Suppose let us say I am cooling one side. Now all the molecules say, no, that fellow is poor, he is not having any, let us give more. So all the neighbors will lose in donation to them. Why? They want to be in equilibrium. That is the law of nature. Why equilibrium? It is a kinetic energy which is equally getting distributed. And you can stop it by insulating, by doing something, you can do. But perhaps that is the one as per the requirement. So this is how the temperature devices are developed in the nature. And let me talk about some of the things. The most obvious, liquid in glass, well before 16th century perhaps, 17th century. The people started working in the 17th century. By the beginning of 18th century, people were measuring the temperature of the human body and atmospheric temperature. They thought those two are the ones which are very important. And liquid in glass, they were using some kind of oils. Why oils? Thick oils are non-evaporative. That time they don't have a technology to seal the thermometer, etc. It is open. If you take a alcohol, what will happen? Everything will evaporate in no time. So that's how liquid in glass, only oils which are highly viscous and less evaporative, they were used as a thermometric substances. But their change in volume was very little. Accuracy was very bad. Then slowly people looked for those which have a more sensitivity towards the temperature, more kinetic energy of displacement. Okay, so that's how there was in search of this one. The next important, same volume expansion, if I use a solids instead of liquids, you can get a bimetallic strips. So most of you, all of you have used the iron boxes. In an iron box, whenever you set to a one, it connects, disconnects. It connects and disconnects. Why? Because there is a strip. So whenever it becomes hot, it gets disconnected from the electrical contact. So the moment it comes back, it will come back so that your cloth will not get burned. And unnecessarily continuously heating, you imagine, you want to iron the cloth and the cloth requires some amount of heat transfer and you are giving some other heat through I square R heating. What is the guarantee that the amount of heat you are consuming into the iron box is exactly what is required for the cloth? Now, when I don't know what to do, if I continuously connect it, what will happen? The temperature of the iron box will increase. Unknowingly, every shirt will get burned. So that's why what should I do? So I should know what is the temperature at which cotton burns. What is the temperature at which polyester burns. So that's how the designer will give you small cutoffs. What will happen? Whenever I'm ironing the polyester, I'll set in the polyester and automatically there is a connection which changes its length. Those are called bimetallic strips. You see this one? Without a proper temperature measurement and control, you can't have an obvious iron box. Otherwise, what will happen? You have seen the roadside iron box people in a villages who will use a burning coal and smoke. Anybody cannot use those things. A typical person who does a good ironing with that systems, he requires at least 2 years of experience. Why? He can understand how to control the temperature, how to pour a water. Sometimes he pours water continuously to control the temperature. And when it goes cold, he'll supply some air. Can you do so much if you want to use same iron box as a home appliances? Can I get a 2 years training only for ironing, 2 years training for using the mixie, 2 years training for refrigerator? Then nobody will buy any appliances at all. Your development will be meager. Very important. Such a powerful things are possible. Similarly, later people developed the gas thermometers because ideal gas has such a beautiful sensitivity. You see this one? There are 3 phases of the substance fundamentally. All the 3 phases, their volume is a good function of temperature. So that's how when it is a liquid, volume change I will use as a measure of temperature. When it is a solid, length itself is sufficient. When it is a gas, not either volume or a pressure, both can be used. Okay, so that's how gas becomes a more sensible than the liquid. Liquid is more sensible than the bimetallic, but everywhere I cannot use gas. Everywhere I cannot use liquid. So sometimes I have to depend upon the solid materials also. All the 3 phases of materials will be used as thermometric substances. Of course, all solids may not be used. There are some solids which have a highest sensitivity to the temperature. They are used. Those are the metals. And these are not sufficient. As I said it, no, I need a temperature property, the property, thermometric property, which will create a digital signal, something like a DC voltage. If I have a DC voltage between 0 to 5 volts, I can immediately digitize and send it to the computer. Then I can read from very far. So that's how I need to depend upon some properties which are more helpful for storing in a memory. Sometimes whole night the system is working. I don't want to read immediately. I want to wait for a while. Tomorrow morning I want to read the record. So this computer will record the entire year. Morning somebody will come to the duty and see what happened at the night. If everything is okay, okay. If there is something deviating, then he will go and correct. Or sometimes there could be automatic control even. The decision making will be good. You need to imagine this particular point. If a body is isolated, there is a question. If the body is isolated from the surroundings, its temperature will increase continuously. Now the thing is, where is the energy which is making the temperature to increase? Are you talking about a human body? Suppose if I have a human body, let us understand that in an ordinary temperature, you will have a very thick blanket and cover yourself. Don't you feel hot? And you will go mad. You may get a fever. And eventually there will be a problem of your entire body process freezing. Yes, a body which is isolated from the surrounding, within the body, if there is an energy resource, obviously the temperature will increase. Or sometimes there may be a body where the process is endothermic. It absorbs. Then the body temperature will go to 0 also. Okay, so first you should know what is responsible for increase of temperature? Is there any action which is creating so much heating or energy which is leading to temperature? If yes, yes. Good example is when it is not, when it is a warm in a summer, you cover with a thick blanket. What will happen? Within 1 hour, you will get a fever. Sorry. Okay. You got the point? You got. Yeah.
Sir, actually, you took like temperature rise is due to the molecular motion inside the body. So whatever atoms and molecules are there, they move, they interact with each other, due to which the temperature increases. So suppose, sir, if inside a human body, if we are isolating it with the surrounding, then temperature should continuously increase.
No. Sorry. Please understand my point very carefully. What I am saying is why temperature is increasing. What is actually temperature I am explaining. If the temperature increases, the increase in temperature is because there is an increase in microscopic kinetic energy of the particles. They'll vibrate with the high amplitude and hit and give it to the other. Now the question is, how come their kinetic energy is increasing? It cannot come from heaven. Why their kinetic energy is increasing? Because, as I said, no, I am taking a solid, heating from this side. Because there is a heat transfer from this side, all the molecules close to this one, they are getting the high kinetic energy and vibrating with a high amplitude and hit the next one. So very important, what is causing the increase in temperature is different from what is temperature obviously. So unless there is an increase in internal microscopic energy, kinetic energy, there can't be a change in temperature. Who is making this temperature to increase is a different aspect. So I'm not discussing about the cause of that microscopic energy. What I want to say is why temperature is so obvious, so important, so tough. Because the temperature is a measure of microscopic kinetic energy of the molecules. You got point? I'm only talking about what is the temperature. Why it is occurring, that is the one where we will go for first law, second law and talk about who is responsible for this action. First you should know what is this, how to recognize this. That is very important before knowing who causes this one. Are you getting my point?
Yes, sir. Actually, okay. Sir, I was saying that. Hello.
Yeah.
So I was saying that sir, suppose there is no interaction with outside, then maybe the body's kinetic energy or molecules kinetic energy may increase or maybe decrease also.
Yeah, depending on internal reaction, no. In the body, suppose if I take a human body, I have ate some food, there is a continuous metabolism happening. That metabolism releases the heat, and that heat is increasing the molecules amplitude and the temperature. Now if I open myself, there is a fan, there is a heat transfer, then my body temperature will be in control. And if not, what will happen? Suppose if I cover with a blanket, what will happen? Internal, there is a metabolism that is trying to increase the amplitude of all the molecules, and my body temperature is increasing. But as a fool, I am not letting it to reach equilibrium with the or maintain my body temperature. Now the brain will think what to do, then it will pump a lot of water through your pores and try to evaporate and take some heat. Even if you cover also, evaporation will cool it. If that is also not helpful, you see this one, within 1 hour in an ordinary environment, if you cover with the blanket, your body will become hot. You will get a fever obviously. Why? There is a metabolism which is feeding it to the molecule. If there is no metabolism at all, if you have a temperature, if I isolate, my temperature will remain constant. Why should it increase? There is nothing feeding the energy. Okay? One more question? Yeah. Huh? Is it possible to analysis in terms of quality in thermodynamic? Okay. See, as a human, no, let us say there are some Ayurvedic doctors or some general things. Suppose if you go to the industry also, there will be some mechanics who will not use the numbers at all. They'll see the color, they'll touch it, is this okay? And because of their experience, no, they have tuned their body senses who will qualitatively say it is okay or not. In fact, it is only the human most of the times or a living species take a decision based on the qualitative approaches. No doubt in the mind he is getting some signal, but he cannot translate into quantitative. What I want to say is, suppose if I have this particular one, I can say whether it is a hot or a cold. What I am doing, I am qualitatively comparing with my body temperature. If its temperature is higher than the body, I will say hot. If it is colder than my body, I will say cold. This is a qualitative description and I am analyzing. Now I will say, whenever this is a pen, somebody say, no, pen should not be this hot. It is wrong. Qualitatively, I rejected it. I have taken a decision. Somebody say that, no, pen should not be so cold. Your fingers will get affected. There is something wrong with this pen. There may be something happening inside. Okay. So these decisions are qualitative. Okay. So you see the good, beautiful thing. The people invented a ballpoint pen. Can I get any ballpoint pen? See, the people were developing the pens, and these pens are made of metallic. A common student, no, he was trying to write it carefully. He is pressing a lot, because of which the biocells are getting ruptured. And qualitatively somebody understood that this is dangerous. If you see, most of the pens will have some rubber material which will get compressed and gives a less reactive pressure on the biocells, and you get the grip. At the same time, your biocells will not be. Don't you think this entire thing is a descriptive field? Suppose if you use this is a metallic, wrong example to say that this is wrong, and if I hold it for a long time, I get pain. Suppose if it is properly covered with some compliant surface, I'll have a beautiful. These are all qualitative decision makings, qualitative analysis, qualitative feel. Okay, so intellectuals, living species take a decisions qualitatively. A dog may take a qualitative decision, and all of you know, some of the bulls, they get offended by any red color. So without knowing whether it is a danger or not, by seeing a red they get offended. Okay, so because it's a qualitative decision, they don't know it is red, no doubt. Is it the red precisely a danger? Means they are not adding any quantitative information. So every living species have such a feel, and many a times they take a right decisions, but they are immature, no, they take a wrong decisions. We say, no, in our brain there is called a medulla oblongata, which takes a wrong decision. Kabhi you see a rope, you think that it is a snake, because it's a qualitative decision, you may get confused. Okay, next question. That's all. Okay, thank you. And now I want to say 2 points here. We are on vacation, as I said, no, I'm going to Bangalore to deliver a lecture. I'm not available in coming week. So our next lecture will be on 11th March. This is number 1. The number 2, what I'm saying is how to measure temperature, how to measure pressure or anything, I'll not discuss. And if you wish, there is a MEL 140 on my website. If you go to my website, I have given my website address. You go to You go to my website, you will get a course MEL 140 Engineering Thermodynamics. Okay, there now I have a full slides which explain the temperature measurement, procedure, calibration, similarly manometers, types of manometers, etc. But as a general class, I want to spend now time on leading to actions and first law. So after the break of 1 week, on 11th of March, we will start how do I use this knowledge? Why should I know the pressure, volume, temperature, how it helps me, and all the reasons which we can control or create by knowing this knowledge we'll discuss after the break. Thank you very much.